So, as per instruction, I have to again introduce myself. So, myself, Sripan Mandal, I am working at ITBHU as a Prime Minister Research Fellow, and I have to, or I was taking for a while this course in which I am conducting some live sessions where I am solving the assignment problems from previous year for this course, Computational Physics, with hoping that these sessions will be helpful for all of the attendees uh, in the live session as well as through YouTube's, so that they can easily solve the assignments in this year. So, and we are in week 8, in which we are going to see how the Laplace equation can be solved numerically. So let's say if you have a one-dimensional, just a second. So a Laplace equation, we have to solve it. So if we have just a one-dimensional problem, then we solved the differential equation in those cases, or we have just one, let's say, just one independent variable in the form of x. Then we solved a differential equation for, let's say, a dependent variable capital X, which is a function of small x. Then we solved them, right? And also we solved second order differential equation, in which we show that we have to transform the second order differential equation in a two coupled first order differential equation, and then we can solve them using RK4 method, as well as the Euler, modified Euler, improved Euler can be used for solve those equations. Now, if instead of having just one independent variable, if we have two independent variables on which the dependent variable will depend, then we have to think of partial differential equation instead of ordinary differential equation. So let's say earlier capital X is just depending upon small x. Now if it is depending upon small x and y, if we are thinking of 2D problem, and if generally if we think of the three-dimensional problem, let's say that in that case capital X is a function of x, small x, y and z. So in this problem what we have is a 2D plate. Let's say what we have is a 2D plate, this kind of a square, because in x and y axis each one of them have 34 cells. So let's say this is 0 0, and then if this is the x axis, then this will be 34 comma 0, this will be 34 comma 34, this will be 0 30, right? And as per the question, what is there, that there is no time dependence of temperature T. So whatever the solution we have for this Laplace equation will be a static solution that will not change with the time. Okay, so to find out at different points, so what we have in this plate, we have all the grids, right? 30 floors got 30 floors, that will be like a matrix, and each one of these points will have a value of temperature. So instead of continuous distribution of temperature, we will have the value of temperature at some discrete points throughout these plates, and those discrete points will be evenly spaced. So as a input we have the value of temperature at the boundaries. So see, if we are solving Laplace equation, we can have boundary condition in terms of Dirichlet condition, in which we are having the value of independent variable itself at each of the boundary points, right? So in this case what we have, that at x equals to 1, let's say the temperature is given for 3.7. so which plane is this? So let's say instead of 0 0, this is starting from 1 and 1. So in that case, for x equals to 1, so that means this line going upward, you have at all the points along this line, the temperature will be 3.7 for whatever the value of y in this direction. Also at x equals to 34, you see that for all y, so that means along this line or along this direction, you have temperature assigned as a value of 0.4. so here it is 3.7 at each one of the point, and here it is 0.4, and we have two other sides left for discussion. So at y equals to 1, now this is like this line, right? And for each one of the x, you don't have one particular temperature. Instead of that, what is happening, that the temperature at x equals to 1, so x equals to 1, it is at 3.7 initially. So here the temperature is 3.7 along this direction, and the temperature is decreasing linearly to have a value of 0.4 at the end point along the direction. So we have to find out an equation which will give us the value of temperature at each of the points aligned to this boundary by some equation, right? So how we can get that? It is decreasing linearly, so we can use that equation like say y minus y1 by x minus x1 equals to x2 minus x1 by, sorry, this will be y2 minus y1 x2 minus x1. So from there on, what we can get is y2, let's say this is the 0.4, right? So this will be 0.4 minus y1, so that will be 3.7, and x2 will be 34, it will be minus 1. So this will essentially 0.1 with a minus sign, okay? So this will be the slope, and what will happen is y minus y1 x minus x1. So in this case you see that you have to calculate y, right? So that will be essentially this into x minus x1 will be, in this case, is 1, and with that you have to add the y1, and y1 will be 3.7. But while writing in the code, this is not exactly the thing which we are implementing. You are writing the equation in such a way that we can have the values which are decreased by 0.1 at each of the steps, okay? So we can see from the program later on. Also we have another point in which the 34, y equals to 34, again along this the temperature is decreasing linearly as it is decreasing in this way. So also the limit of convergence is 0.0001. So what does it mean by limit of convergence? So basically what happens, as we are going to make the steady state in each of the point or throughout the plane, so it means that if we are having a number of iteration, so from one iteration to another iteration the temperature distribution is changing, and that temperature distribution will keep changing until the total plate assumes, or the total plate reaches a state in which the temperature distribution is steady as well as in equilibrium. So how can we achieve the equilibrium numerically? So basically that is the limit of convergence, that if at let's say ith uh, iteration the temperature at each of the points has some value, let's say Ti, right? And if at I equals I plus 1 it will have another value, let's say Ti plus 1, then we can say that it will converge if Ti plus 1 minus Ti, that will be less than or equals to 0.0001. So till then we will run this code, or we will iterate this code by steps, and as soon as the code will reach in this or match this property, it will be stopped or it will be exited from the loop. Okay, so then we have some questions. We have 4 questions total, in which we have to calculate the temperature at different lattice points. For example, in the first problem it is 10 10, and in other problems the lattice points are just changed, and what we have to do, we have to calculate the temperature at those lattice point after convergence. So until the convergence criteria is reached, we have to continue iterate the solution of Laplace equation starting from this boundary conditions, and we can assign the values within this plate to be 0 for the temperatures at the points except the points at boundary. So Dr. Shahid, is it okay for you till now? Hello? Hello?
Hello.
Yeah, is it okay for you?
Yeah.
Okay, fine. So let's move on to the numerical, I mean algorithm part. Okay, so just I have to open another window. So before that, just a second. Okay, so here comes the program. Is it visible? This program Laplace.f.
Yeah.
Okay, fine. So what I have done, that initially, as always, we have to consider that implicit none, and then I am assigning all of my variables its type, whether it is integer or double precision or real anything else. So we have 34 by 34 plate, so I am assigning that okay, Lx is 34, Ly is 34, so that means the number of grid points at x and y direction. And then what I have is a temperature array, which is a two-dimensional array because it will depend as x and y both. So old t and t. So old t is basically, we are, since we are doing it is iteratively, then I have to assign that okay, at a particular iteration we are going to calculate the value of t at each of the point, and then I am going to assign that temperature array to old t, and that will be used for the upcoming iteration. Okay, so in each step we are going to update the value of temperature at each of the grid points, and I will assign those values to this array old t, and in this way the temperature array will be updated until the convergence criteria is satisfied. Okay, so the other things are also given here. So I have assigned that okay, the dt, the increment in the temperature that will be like 0.1, and old t, that is essentially given to be point 0, I mean 0 is initially. Then what I did that, okay, so now all of the elements in the old t array is assigned a 0 value, but we have the boundary conditions. We have to implement those boundary conditions within our program. So initially what I am trying, that let's say I am fixing the value of x at 1 and 34, and I am assigning the constant value of the temperature in those two regions. So we have for the question that when x equals to 1, whatever the value of y, we have a temperature value of 3.7, and at x equals to 34, whatever the value of y, we have the temperature value to be 0.4. So we have assigned those two boundary surfaces, right, or boundary lines, and then I am going to assign the temperature values at two other boundary lines. Okay, so in this case what I am trying to do, I am fixing the value of y and I am changing the value of x from 1 to lx, and then that is given by this way. How this is going to work? So basically you see in the problem it was given that the temperature is starting from 3.7 and then it is decreasing to 0.4. So if it takes the I equals to 1 value, so what it will do, that let's say it is taking I equals to 1, and at I equals to 1 what value we have to have, that will be 3.7. so if it is 1, then d float it will be given me just 0.1, so there is the decrement, right? So 3.8 minus 0.1, that will give you 3.7. and in the similar way, if you reach the lx point which is 34, so then it will be 3.4 is subtracted from 3.8 and that will give us 0.4, and that is the question suggesting. And in the same way we can have that profile of temperature at the y equals to 34 boundary line also. And then what I am doing, that we have another array which is t array, the temperature array. I am just assigning this old t array to temperature array, and then I am firstly what I am doing, so before the iteration starts, I am going to store all of the values, the temperature values at initial stage. So that will give us that instead, or sorry, just at the boundary there are some finite values except 0 for the temperature, and at each of the points which are interior to the boundaries, at that points the temperature will have values 0. So we are going to write the temperature distribution as well as the grid coordinates in a file which is initialize I0 dat, so that will store all of the values at the initial stage before the steady state solution is reached, or before the iteration for the steady state solution, for achieving the steady state solution is just starting. So we have given stored those values in a file. Then I am assigning that, okay, test equals to 0 and counter equals to 0. So counter is going to count how many iteration we needed for for achieving the steady state solution. So we have open a do loop which is an open do loop. That means it does not have an premeditated or premeditated condition for stop. So it will depend upon the convergence criteria, that how much this do loop will work on. So after that what happens is, so at each step counter is have a value at a particular point. Let's say it is starting from 0, and then at each iteration it is going to increase by 1. and also we have a criteria that taste is assigned a value of 0. So and if taste equals to 0 is met, then we are going to stop our iteration. So okay, so now we have a 2D array which I have to calculate as the solution or the iteration is going on. So how do we going to calculate is that we have a formula, right? So how that formula is working, just a second. I have to off speed, sorry. Yeah. So what we have is, let's say, del 2 t del x2 plus del 2 t del y2 equals to 0. So this is my Laplace equation. Now so in we have a 2D array, right? So I comma j. So if we have to calculate this Tij at a particular grid points, so it will be assigned or it will be calculated like this 1 by 4. Then it will have these values, that t I plus 1 j plus t I minus 1 j plus t I comma j plus 1 plus t I comma j minus 1. So this is the nearest neighbor points for ij, right? So you have, let's say this is your I j point. So this will be like I plus 1 j point. This will be I j plus 1 point, and here it is I minus 1 j point and I j minus 1. So for updating this the temperature at this point, we have to use the temperature values which are evaluated at the early at the just the before it the iteration just before the present iteration at these points. The four neighbor points are used, and that will be added to each other, and we have to divide that by 1 by 4. So if we look at the code, just a second. Yep. So if we look at this code, what I did is t1, that is going to I minus 1, I mean ii is there for the loop parameter, and I plus 1, and then in I have just written it as in this way, 0.25 is 1 by 4. So in this way I am going to calculate the temperature at each of the grid points. And then what I am doing, so again I am going to check the convergence criteria, right? So in this 2j 2 ly minus 1, and if absolute is greater than is 0.0001, then I am going to say that okay, taste is equals to 1, and I am continuing the loop until the convergence criteria is reaching. So then if taste is equals to 0, then it will exist. Also at each also the temperature array will be assigned to old temperature array at each of the at the end of each iteration, and then I am going to write the counter that is the number of iteration it will need to reach the convergence. And then again, at the end of the convergence, I am writing all of the values of the temperature at each of the grid points at a different file. Okay, so now the code is understandable. Hello. Hello. Dr. Shahid.
Yeah, yeah, carry on.
Yeah. So any problem till now?
Hello?
Any problem till now?
No, no, no.
Okay, fine. Okay, so we have 4 questions in which the lattice point is just changing. All of the questions are same. So we have to calculate, or we have to estimate the temperature value at 10 10. That means at a lattice point which have grid coordinates 10 10, as well as in 14 11, 30 30, and 18 18. So we have the code which is understandable till now. So let's move on to the execution part. So I'm going to open my terminal, and so we have the code named laplace.f g-fortran laplace.f. So it is compiled dot slash dot dot. So here are the answers. So we have t at 10.10, it will be 2.799. Now if we look at the answers, just a second. See, the first question is the temperature at lattice point is 10 10 after convergence is. So we have these solutions, and if we look at the answers, this will be the correct answer. So the answer was coming to be 2.799, and this is the closest of the options to that answer which you are getting. So the second question, we have the lattice point changed to 14 11, and if we look at the answers, so this will be 2.399, and the closest one is 2.383. So this will be the correct answer. For the third case, for 30 30, it will be the 0.79. So that will be 0.797 will be the closest answer for this question. And for the last one, it is 1818. In this look that 1.99 is the answer which we are getting after compiling our code. So 1.978 is the closest answer for this question. So these are the 4 questions which I have to solve, or I had to solve for this session. So I hope you have any problem. Either Dr. Said, is there any problem?
No, no, no.
Okay, so
Thanks.
so you understand everything, right?
Yeah, yeah, yeah.
Oh, okay. Thank you. So I don't have anything else to say for today. So you can stop, and I will meet on next Sunday as per usual schedule.
Okay.
Okay. So thank you.